Hello everyone. In this video, we will discuss graph theory. Now, firstly, what is graph? Now, first of all, let us take a street map of our city, and we put a dot at each place where two or more streets come together at or they end at a dead end. Now, what we will get? We will get an example of what we called a graph. So some of the streets, basically they are one-way streets which permit traffic in only one direction. So we put arrow in that one-way street which indicate the permitted direction of traffic flow. And we put a double arrow for the two-way streets. So in that case, we will get a directed graph in which the directions are given, in which direction that street permit traffic. So basically, graphs provide mathematical models for a set of objects that are related or bound together in some way or some other way. So graph theory basically is basically abstract mathematical phenomena, but when we represent any graph by a geometrical diagram, then it is just like a geometrical phenomena. So first of all, we define graph. A graph is composed of two type of objects. So we define graph as a graph, say G, we will denote graph by G, or this graph is called simple graph also. Graph G is composed of two type of objects. One is a finite set V, which we denote like this, A, B, C, and so on. So this is a finite set, and this set is called set of vertices. And other is set E of pairs of distinct vertices, means distinct elements of the set V. And we call these pairs of distinct vertices edges. And these called edges. So we denote the graph G, whose vertex set is V and whose edge set is E, by G is pair VE. And number of vertices in the set V is called the order of the graph. The number of vertices in set V is called order of graph G. Now if we take alpha is equal to the pair xy or yx, if this is an edge of G, because E is set of pairs of distinct vertices. So if we take alpha, an element of E, which is the pair xy, then we say alpha joins x and y, because here x and y, they are vertices and alpha is edge. So alpha joins x and y, or we say that x and y are adjacent, means there exists an edge between x and y. So we say these are adjacent. And we can say that x and y are incident with alpha, or we can say x and alpha are incident, means the vertex x is incident with the edge alpha. Similarly, the vertex y, this is incident with the edge alpha. Or simply we can say that x and y, they are the vertices of the edge alpha. So from this definition, we can easily see that graph is abstract mathematical entity. But we can think of a graph as geometrical entity by representing it with the diagram in the plane. So we take distinct points as the vertex points, and for each vertex we connect two different vertex points by a simple curve or by a line if there is an edge between that 2 points of the graph, and we label that edge by alpha. So that's how we can assume that this is a geometrical entity. For example, if we have a graph G, which is given by, let G is a graph VE, where the set of vertices V is given by A, B, C, D, E, means there are 5 different vertices, and E is given by this set AB, BC, CD, so let us say DA, EA, EB, and ED. Suppose this is our set E. Then how can we represent this graph geometrically? So we firstly mark these vertices as different points on the plane. Let these be points A, B, C, D, and say this is E. Then we draw a curve for this edge from A to B. Now this is edge A to B. So for that we draw a curve like this, B to C, then we draw B to C, then C to D, then for this edge D to A, we have this edge, then E to A, then E to B, then E to D. So this is the geometrical representation of this graph. Now if we allow a pair of vertices to form more than one edge. Now in this graph, there is exactly one edge between any two vertices. But if we allow more than one edges between any two vertices, then the graph will be a multi-graph. So let us say in this example, if we take one more edge AB and one more edge CD, say these two are also the elements of E, then we have this type of graph. We have two edges from A to B and two edges from C to D. So this type of graph is called multi-graph. Now we define complete graph. A graph is said to be complete if each pair of distinct vertices form an edge. Means if between any 2 points there exists an edge, then we say the graph is complete. So we define complete graph if each pair of distinct vertices form an edge, then the graph is said to be complete. So we can say in complete graph, every vertex is adjacent to every other vertex. So if we take graph of order n, means it has n different vertices, then every vertex is adjacent to every other vertex. So every vertex has n minus 1 edges connected to it. So the total number of edges in this graph, that will be n into n minus 1 by 2, because every vertex has n minus 1 edges adjacent to it, and we have total n vertices, but we know one edge that is adjacent to two different vertices, so it will be divided by 2. So if we have number of vertices n in a graph, and it is say a complete graph, then number of edges in that graph will be n into n minus 1 by 2, and complete graph is denoted by kn. Complete graph with n vertices, that is denoted by kn. For example, if we want to draw K1, the complete graph with one vertex, so that will contain only this vertex, because the edge, to form an edge, we need two different vertices. Secondly, the complete graph K2 containing two vertices, that will be a graph with two vertices and an edge between them. Then K3, it is a graph with three vertices. Now this first vertex have edges joining the other two vertices. This vertex has edges joining the other two vertices. Similarly, this vertex has edges joining the other two vertices. So this is K3 graph, complete graph of order 3. Now K4, the complete graph of order 4, that will be graph of this type. Let us say, now this vertex is adjacent to all other three vertices. Similarly, all vertices are adjacent to the rest of the vertices. So this is complete graph with 4 vertices, K4. Now complete graph with 5 vertices. Let us say these are 5 vertices. Then the complete graph of 5 vertices, that will be of this type. So this is K5, the complete graph of order 5. Now, in drawing these graphs, we can see that there is always at least two edge curves which intersect at a point that is not a vertex point. For example, in this graph K5, if we draw, let us firstly name these points A, B, C, D, E, the 5 points. Now, if we draw this edge from A to E, and then we draw edge from B to C, then these two edges, they intersect at this point, and this is not our vertex point. So these type of graphs are called non-planar. So let us define planar graph. A graph is planar if it can be represented by a drawing in the plane in the manner or in such a way that two edge curves, they intersect only at vertex point. Now we define planar graphs. So a graph G is called planar graph if it can be represented by a drawing in the plane in such a way that two edge curves intersect only at vertex points. Means we can draw that graph such that the edge curves, they will not intersect except at vertex points. That type of graph is called planar graph. So we have drawn the graphs k1, k2, k3, k4 and k5. So in those diagrams we can see that k1, k2, k3 and k4, these are planar graphs, but k5 is not a planar graph. Now we define degree of a vertex. Now degree of the vertex in a graph is number of edges that are incident with x. Degree of a vertex in a graph, this is defined to be number of edges that are incident with that vertex. So if x is our vertex, then we denote it by degree of x. Now if we have an edge alpha, which is given by xx, that means it is a loop starting and ending at point x. Then alpha contributes 2 to the degree of x. If we have a closed loop from x to x, then we say degree of x is contributed to by this edge alpha. So now we define a sequence that is basically a list of degrees of graphs vertices, and we always define this sequence in non-increasing order. So we define a sequence d1, d2, dn. Let us say we have a graph of n vertices, then we define this sequence d1, d2, dn, and all these d1, d2, dn, these are degrees of the different n vertices. And this type of sequence is always defined in non-increasing order. That means we write the numbers d1, d2, dn in such a way such that d1 greater than equals to d2 greater than equals to d3 and so on greater than equals to dn, and this is always non-negative. Now we call this sequence as degree sequence of G. So what is the degree sequence of complete graph Kn? Now degree sequence of Kn is n minus 1, n minus 1 up to n minus 1, because every edge is, every vertex is incident with n minus 1 different edges. So degree sequence of Kn is just this, n minus 1 repeatedly n times. So now we have this theorem which says if G is a simple graph, then this sum d1 plus d2 plus dn, which is sum of all the degrees of all the vertices of the graph G. Now this is always an even number. And moreover, the number of vertices which have odd degree in this graph G, that is also even. So number of vertices of G with odd degree, that is even. Now to prove this theorem, we can say that each edge of G contributes 2 to the sum of the vertex degrees, because if we have an edge from x to y, then that edge contributes 1 to degree of x as well as to degree of y. So every edge contributes 2 to sum of vertex degrees. That means sum of and we know if a sum of integers is even, then the number of odd integers summed, that must be even. So if there are, let us say, vertices whose degrees are odd, so but we are saying that uh, total sum of degree sequence that is even. That means there are exactly even number of those type of vertices which has odd degree. So to prove this theorem, we can simply write like each edge of G contributes 2 to the sum of degree vertices. So that's why sum of all the degrees that is even. Now we have an example. Let us say at a party, a lot of handshaking takes place among the guests. Now we have to prove that the end of the party, the number of guests who have shaken hands an odd number of times, that is even. Now in this example, we assume that now this can be done by multigraph. Now here we assume that the guests at the party, they are vertices of our graph, and each time whenever two guests shake hand, we join them by an edge. So we get a multigraph, and to this multigraph we apply this theorem d1 plus d2 up to dn is even. Now, because the number of guests who have shaken hands an odd number of times, that will be, by this theorem, that will be even. So now we define isomorphic graphs. So now we define isomorphic graphs. So let us say we have two different graphs, G, which is VE, and G dash, which is V dash E dash. Then these two graphs are called isomorphic if there is one-to-one correspondence theta from V to V dash between their vertex sets, such that each pair of vertices xy of V, for that pair, there are as many edges of G joining x and y as there are edges of G dash joining theta x and theta y. So we define two graphs. One is GVE and other is G dash V dash E dash. They are called isomorphic if there exists a 1-1 correspondence. First of all, there should be 1-1 correspondence from V to V dash, 1-1 correspondence between the vertices set. And this is corresponding such that for each pair of vertices, say x and y, of the set V, there are as many edges of G joining x and y as there are edges of G dash joining theta x and theta y. Now this 1-1 correspondence theta, that will be called isomorphism of G and G dash. Now here the isomorphism means sameness. Isomorphism means simply the two graphs are simply, they are similar, they are same. So from this definition, we can see that two graphs are isomorphic. First of all, if they have same number of vertices, means there is 1-1 correspondence between B and V dash. And secondly, if there are, let us say, n edges between x and y, which are vertices of the set V, then there should be exactly n edges between theta x and theta y. Then only we can say that the graphs are isomorphic. Now, if we have two graphs G and G dash, then we can express the fact that the two graphs are isomorphic by asserting that there is a 1-1 correspondence between the vertices set V and V dash, such that whenever two vertices of V are adjacent in G, the corresponding vertices are adjacent in G dash. So, for example, let us take these two graphs. Here we have four vertices, let us say A, B, C, D in this graph, and one more graph we have like this. Let us say these are vertices P, Q, R, S. Now we are saying that these two graphs are isomorphic to each other. So let us see how. Let us take theta, the correspondence from set V to V dash, which maps A to point P, B to Q, C to R, and D to S. Now, if we take this correspondence A to P, B to Q, C to R, D to S, then we can see here there is an edge from A to D. So there should be an edge from P to S, and that is this. Similarly, there is an edge from A to C, so there should be an edge from P to R, and that is this. Then there is edge from A to B, so there should be edge from P to Q, and so on. Similarly, we can see whenever there is an edge between these vertices of set V, then correspondingly there is an edge between the vertices P, Q, R, S. So these two are isomorphic graphs. Now basically these two graphs are just representations of K4, the planar graph K4. Now in this representation we can see that any two edges, they are not intersecting except at vertex points. But in this representation, these edges PR and QS, they are intersecting at this point, which is not a vertex point. But still this is a planar graph because it can be represented by this geometrical representation. So these two graphs are isomorphic to each other. So from this conversation, we can conclude that isomorphic graphs have same order and same number of edges, but the converse need not be true. If two graphs have same order and same number of edges, then they need not be isomorphic. So let us see how. Now we take these two graphs. Now in this graph, we have 5 vertices A, B, C, D, and E. Now one more graph we will take. This graph also has 5 vertices. Let us say this vertex P, Q, R, S, and T. So we have now two graphs. Both graphs have same order. And this graph has how many edges? 1, 2, 3, 4, 5, 6. So this graph has 6 edges. Similarly, this graph has also 6 edges. 1, 2, then 3, 4, 5, 6. So both the graphs has 5 vertices and 6 edges. So same number of edges and the same number of vertices, but still they are not isomorphic. Because in this graph here, we have this vertex A, which is incident with only one edge. But in this graph, there is no vertex which is incident with only one edge. So these two are not isomorphic to each other. Now, one more thing we can say about these isomorphic graphs, that the degree sequences are same. So from this example, we are saying that number of edges and number of vertices are same, but still they are not isomorphic since their degree sequence is not same, because degree of A is here 1, but in second graph there is no point of degree 1. So we should say that degree sequence should be same of two graphs to become an isomorphism. But still we can say that if two graphs are isomorphic to each other, then the degree sequence is same. But if degree sequence of two graphs that is same, then still we cannot say that the two graphs are isomorphic to each other. Now let us take this example. Now this is graph A, B, C, D, E, F. Graph consisting of 6 vertices. Now one more graph we have, again with 6 vertices. This is P, Q, R, S, T, C, U. So if we can see here, these two graphs have same number of vertices, same number of edges, and same degree sequence, because every vertex here has 3 edges incident with it. So the degree sequence of both the graphs, that is 3, 3, 3, 3, 3, 3. But still they are not isomorphic to each other, because here we have this set of points A, E, and F, such that F is adjacent to A and E, A is adjacent to F and E, E is adjacent to A and F. But here we do not have set of 3 points which are adjacent to each other. So these two graphs are not isomorphic. So we have necessary conditions for two graphs to be isomorphic, that their number of edges, their number of vertices, they should be same, their degree sequence should be same. But this is not a, these conditions, these are not sufficient conditions for the graph to be isomorphic.